All right. Good morning. And welcome to whoa. Oh, there we go. Welcome to morning 3. All right. Oh, let's mute the volume, that way we don't get a sound delay. All right, we're live. Lecture doesn't start for another 5 minutes. I am going to at least the plan is I'm going to be attempting to start our live streams 5 minutes ahead of schedule from here on out. Just to kind of give us a chance to say, hey, what's up? If you guys have questions, concerns, procedural things, I'm going to continue to address all of the kind of class business at the end of the video. Like I've been doing so far. We've only done 2 of these, so we haven't really established a convention. But I kind of like hitting the informational stuff, class informational stuff, at the end, starting with lecture, getting that finished and done with, and then after we're done talking about chemistry content, some people have to move on to another class, but dealing with kind of the procedural stuff, due dates, exam dates, all that after the lecture is over. And then for those of you who've come back, my English is super good this morning. Those of you who've returned to look at the videos again, you can see that in the comments I outline with links to the time signatures in the video where everything is. So you'll see, like, oh, we started discussing light at 5 minutes in or whatever, and then at the very end it'll say questions and class info right at the end of the video. So you'll be able to skip, just look at what's up there. So here, I've just got live streams written here. I'm going to be beginning live streams like 5 minutes ahead of lecture. From here on out, see how that works. That way you can, lob your questions, like, go, I've got a question about this, and then I kind of know what we have to discuss at the end. And, it's a time where we can say, hola and what up, share our new favorite emojis. I don't know what you guys have been doing during your COVID quarantine, but I've been watching My Hero Academia with my kids and my brother. We've got this weird amalgam. I've got my 9-year-old who's in 4th grade, and 11-year-old who's in middle school, and we're all home and quarantined now. But I also have my brother who's in his last semester at UC Berkeley, who's quarantined with us, and we've all been watching anime together, My Hero Academia, and I've decided, if you know the show, there's this character named All Might, and I've been texting all of my family All Might gifts. That's my new thing to get through quarantine. Oh yes, okay. So Vraj has been using this quarantine time to study for the MCAT, which is incredibly appropriate. Speaking of appropriate, our song of the day. Our song of the day is Lazaretto by Jack White. Which is about or inspired by leper colonies. Lazaretto. So you can check that out. I'll drop the link in the info about the video when I go back and do the outline. So hopefully your Monday is finding you alive and well, though our concurrent viewers is going down. So either people are a little late to the party, or maybe we're succumbing to coronavirus, or Maybe we're caring less. Who knows? So we're gonna go ahead and dive in, start talking, continuing our intro to quantum chemistry, and then we will talk a little bit about exam 2 at the end of lecture. All right, so where we left off on Friday is we were talking about light, specifically that if you took the wavelength of a photon of light and multiplied by its frequency, that it would equal a constant number c, and that c is the constant speed of light. Which we said on Monday was 3.00 meters per second. It doesn't matter what type of light you're talking about, visible light, ultraviolet, X-ray, infrared, all light waves travel at the same speed. Okay, first mistake of the day. I wrote 3 meters per second. That is not the speed of light. The beauty of working in Photoshop is we can use the lasso tool to correct our mistakes. 3.00 times 10 to the 8th meters per second. How about that? It's a way more accurate speed of light. All right, now, so all light waves travel at the same rate, but that does not mean that all light waves have the same energy. The energy of a photon of light is actually directly proportional to its frequency. So, whoa, okay, there's the downside of working in Photoshop. Sometimes it thinks your hand is the pen. Energy is directly proportional. The energy of a photon of light is directly proportional to its frequency. And as we know, we can convert this proportional to an equal sign if, oh goodness, let's erase that. We can switch this to an equal sign if we multiply one side of this equation by a constant. And the constant here that you use is something called Planck's constant, or I think it's Planck, probably officially. So this guy right here is it's spelled Planck, like walk the plank, but I've heard people say Planck, because I think he was German. Actually, I know he was German. Now, if you think about what type of units Planck's constant must have, we know that energy has units of joules, right? And we know frequency has units of hertz or inverse seconds. So Planck's constant, in order to make these two equal, has to have units of joules times seconds. That way seconds cancel, you get energy on both sides of this equation. So the units are joule seconds. And Planck's constant has a value of, let's see here, 6.626 times 10 to the negative 34th joule seconds. That is, that is a value for Planck's constant. And with that in hand, again, you don't need to memorize it. The constant or the equation, I'll provide both of them for you on the exam. With those in hand, we can now calculate the energy of specific photons of light based on their frequency. And that brings us to, our first example. Hang on, let me make sure I didn't wreck slide 2. There we go. Okay. All right. Okay, so, all right, our first example. So consider the following example. Oops. So yellow light, turns out, has a wavelength of, where are we? 600 nanometers, and violet light has a wavelength of 400 nanometers. All right. And so the problem asks us to predict which wavelength has a higher energy, and calculate the energy of each. All right. So first, we're asked to predict our wavelength, and we can do that by comparing the two wavelengths. All right. Now you remember that we have an equation that relates both wavelength and frequency, right? It's that the wavelength of a photon of light times its frequency is equal to c, the constant speed of light. And what'll help us compare these two is if we isolate either wavelength or frequency on one side of the expression. When you do this, you'll see that wavelength is equal to the constant speed of light divided by frequency. And this shows us that the reason why I'm writing out this equation is it illustrates the fact that these two are inversely proportional. If wavelength gets larger, that means that let me approach this from the other end. If you have a larger frequency, all right, frequency is in the denominator, so the larger the frequency is, the smaller the wavelength will be. And conversely, the smaller our denominator gets in this expression, the smaller the frequency, the larger the wavelength will be. So when you're asked to determine which is higher in energy, we know that wavelength and frequency are inversely proportional. So we can look at these two wavelengths of light and say, well, the yellow light, because it has a larger wavelength, has a lower frequency, and the violet light has a larger frequency. You're like, how does this help us predict our energy? Well, we also have an expression that we just talked about today, where we see that energy is equal to Planck's constant times frequency. Now, these two are directly proportional. When frequency increases, energy increases. When frequency decreases, energy decreases. So energy and frequency are directly proportional. And since we said that our violet light has a larger frequency, that means that it will also have a larger energy. Larger frequency, larger energy. So we would predict that the violet light's energy is indeed higher. Now we need to calculate to see if that prediction is correct. All right. So first off, let's start with the yellow light. So if we want to calculate our energy, again, remember energy is equal to Planck's constant times frequency. If we want to calculate our energy, we need to know our frequency. And we've been given, the wavelength. And we know wavelength times frequency is equal to the constant speed of light. So we're going to begin by isolating frequency on one side of this expression. That'll allow us to calculate our frequency. So frequency here is equal to the speed of light divided by its wavelength. Now, we're almost ready to plug in to actually calculate a value for our frequency. The problem is, when we do, speed of light is 3.00 times 10 to the 8th meters per second. And the wavelength is 600 nanometers. All right, now the problem here is one of units. Nanometers and meters won't cancel each other, so we need to do a unit conversion. We need to convert either our meters to nanometers or nanometers to meters. It doesn't matter which one. It'll come out fine in the end. All right, here, hang on 1 second. I got to step away from the microphone. It's one thing that never happens when we are lecturing in class is you can't hear my kids when we're in our classroom normally, but I think the microphone was starting to pick them up. Okay, so we need to convert our 600 nanometers to meters. Nanometer. So we need nanometers in our denominator, and we need meters in our numerator. Nano is 10 to the negative 9, so 1 nanometer is 10 to the negative 9th meters. Here, nanometers cancel. And our calculator, my calculator is telling me that when I crunch my numbers, that this will be 6 times 10 to the negative 7 meters. All right. And when you look at your significant figures, you'll notice that 600 nanometers has 1 sig fig. Our answer has 1 sig fig, so we do not need to round or add any decimals or anything. We're good to go. And now that our units are consistent, oops, not there. Now that our units are consistent with each other, we are we're good to crunch our numbers. So frequency is equal to 3.00 times 10 to the 8th meters per second divided by 6 times 10 to the negative 7th meters. Here, meters cancel. And ready to punch this in. So busting out my calculator. We've got 3.00 times 10 to the 8th divided by 6 times 10 to the 7th. So this comes out to be 5. My calculator is telling me it's 5 times 10 to the 14th. All right. Now, sig figs wise, we have 1 significant digit in our denominator, 3 in our numerator. Because we're dividing, we got to roll with the lower quantity. So our answer is 1. So we're good. We're good on sig figs. Yeah. So this is yes. Okay. It said that okay, so sorry, questions. It says this conversion won't be given, right? And that is correct. The unit conversions that are part of the metric system, so like kilo, centi, milli, micro, nano, pico, and femto. Those are the ones that you just need to know. So I will not provide metric unit conversions. So So it'd be good to know those off the top of your head. Though honestly, now that we're in a digital situation, memorization, it'll help you get the problems done faster. So in the timed multiple choice part, it'll be useful. But for the take home, you'll have all the time in the world. So that probably matters less now. All right. Now we have the correct value. We have the correct sig figs. What about our units? Now you'll notice this is something where it's easy to make a mistake. It's easy to see that, our meters canceled. The only thing left in the expression is seconds. But if you wrote your answer in seconds, it would be wrong. Your units in seconds. Your units here are 1/seconds. All right. That's because frequencies units are measured in hertz. They're a per second unit. So, and you'll see if you wrote this in seconds, you'd have trouble later. So now that we know our frequency, we can use our first expression to solve for our energy. Whoops. Energy is equal to Planck's constant times frequency. Planck's constant is 6.626 times 10 to the negative 34th. And the units are joules times seconds. Here our frequency is 5 times 10 to the 14th. And you'll notice that per second, having that second in the denominator, is super clutch because that is what allows this to cancel with this, leaving us with units of energy. So let's crunch our numbers here. All right, our value for energy is, my calculator's telling me it's 3.313 times 10. Let's see. Wait, hang on. 6.626 times 10 to the negative 19th. Now, sig figs wise, Planck's constant is a measured quantity. It has 4 sig figs, but our frequency only has 1, so we can only keep 1. So the correct value with the correct significant figures will be 3 times 10 to the negative 19th, and then our units are joules, and that is the energy for yellow light. All right, let's see. Can we just write the right answer as over S? Yeah, we want to end with joules. You could put the whole value of it as over seconds. So if the question, is right here, would it be correct to write this as 5 times 10 to the 14th over seconds? That is 100% okay. Yeah, that is totally fine to write the answer like this way. And just like Sarah said, we're going to end with joules anyway. So it'll work out in the end. But if you wrote it like that, you're totally solid. Sorry, I'm catching up on the comments here. Let me see. Is this exam caliber? That is my new favorite question. Okay, that's an interesting question. So Raj is wondering, is this exam caliber? We're only halfway done, by the way. We still need to calculate the other energy. Before we went digital, I would say absolutely not. This is too easy. Right? Just like Ace 159 just said. Is that a yes? Sorry, I was a little far away, so I couldn't quite see what your icon was, but I see it's a Pikachu, which is what I was hoping for. Yeah, before we went digital, I would say this is totally not exam caliber. But now, as I'll talk about a little later, there's going to be 2 sections of this exam. There's going to be a take-home written part, and there's going to be a multiple choice. And this is totally multiple choice exam caliber, because those problems are going to be quick, straightforward, just can you do these calculations? And then the take-home part will be the more thinky part. So this is not something I'd write in a problem to have a long answer, but for multiple choice, this is totally the type of problem that you'll see there. All right, so that was the energy of a yellow photon of light. Now let's look at violet. Our violet photon of light has a wavelength of 400 nanometers. And just like with our 600 nanometer wavelength, we need to do a unit conversion. So 1 nanometer is 10 to the negative 9th meters. These two cancel, or the nanometers cancel, leaving us with 4 times 10 to the negative 7th meters. Now we can find our frequency by dividing the constant speed of light by our wavelength, now that we have consistent units. So again, meters cancel. When I take 3 times 10 to the 8th and divide by 4 times 10 to the 7th, I get 7.5 times 10 to the negative 7. And now, sig figs wise, we can only keep 1 because there's only 1 in our denominator. I'm going to wait to round till the end, all right? But I'm putting that line there to remind myself there's only 1, and then our units here are per second or hertz. Now that we know our frequency, we can plug it into this equation, and 6.626 times 10 to the negative 34th joule seconds times 7.5 times 10 to the negative 7 inverse seconds. Our time units cancel, and now we are ready to get our energy. All right, so our energy, the value for energy here is 4.969 times 10. Oh my goodness, hang on. Mistake city. Yeah. Raj got there before I did. So we have, this is because I was doing math in my head, not 7.5 times 10 to the negative 7. This is 10 to the negative 14, which makes this 10 to the negative 14, which makes this 10 to the negative 19. We can only keep one significant figure because of our frequency. So the photon of violet light has an energy of 5 times 10 to the negative 19 joules, whereas the energy of yellow light, as we calculated on the previous slide, was 3 times 10 to the negative 19. So as we predicted, violet light has a higher energy. That is the end of that problem. Yeah, that number was totally totally wrong. I did goof. But fortunately, you guys are sharp, razor sharp. If you were a member of the Wu-Tang Clan, I'd have to call you the RZA, because you're razor sharp with the beats and the rhymes. Okay, so that is an introduction to a light problem. That was a little on the light side, not the hard side, but that makes it a good caliber problem for multiple choice. So any other questions, comments before we dive into the next section? All right. So now that we've kind of had an introduction to light, we know how its wavelength, frequency, energy all interrelate. we're ready to start moving into our true introduction to quantum. The lights. I hate your pun. Well, I'm trying to think of a good comeback, but I really can't. Well, dot dot dot. Cries silently. Okay, so I got a positive 14 there too. Yeah, did I goof up again? Let me go back. Would not be surprised. Yep, I wrote a negative 14 when in fact it should be positive. Whoa, and then it's blobbing. Boop. There we go. Positive 14. Positive 14. Positive 14. All right. Jake, you're spot on. Oh man, quarantine's got to be rough. If you're living for these puns. All right, so. Yes, it's a double goof on this problem. I think it's, you know what, it's something to do with the fact that, like, you're working a softer problem, you're like, this one's easy, I don't have to worry about this, and you kind of, like, coast, but that's when you mess up. Kind of like on a skateboard, you're like, once you start feeling comfortable, that's when you're going to eat it. But when you're working a harder problem, you're like, okay, I've got to have all this stuff locked down. You work those fine, but then you're working an easy problem, and you know, hit the pavement doing something stupid. That is one upside to the quarantine is I've been writing a lot more. That's been nice. Okay, so anyways, so with that kind of intro to light, those of you who have physics in your background have seen all this before, but we needed to make sure we're all on the same page so that we can move into our true introduction to quantum. Now, what? So we had so how do I want to say this? Quantum mechanics arose out of kind of studying atomic structure. So before, tiny rock went under the wheel of my problem, and then it was just tasting concrete. So quantum mechanics arose from a study of atomic structure. Before the quantum mechanical model of the atom took root, we had something called the Rutherford model. All right, and the Rutherford model had protons and neutrons in the nucleus, and electrons orbiting the outside. And even to this day, when we think of when I say the word atom, this is probably the picture that pops into your mind. You've got a little dot on the inside, and that's your proton, your nucleus with your protons and neutrons, and you have an electron that's out in an orbit, just like planets orbit the sun. I actually want to move this electron over. Now here, we're gonna do some audience participation. Sorry. I just saw face plant, and then I saw face plunk, and that was the best. That was the best thing that's happened today, hands down. All right, now we're gonna do some audience participation. I want you to think about this for a minute. I have a question. I have a query for you. Question. Do protons, those are protons who have been hitting the beach, soaking up those rays. Do protons attract or repel electrons? Slowly going insane over quarantine. Do protons attract or repel electrons? That's my question to you. And hopefully, this is a no-brainer. Hopefully everyone's like, oh. Whoa. I hate when Photoshop does that. All right. Do protons attract or repel electrons? Hopefully everyone's like, oh, they attract because they have opposite charges. Attract. All right, now I'm feeling spelling insecure. No, there's 2 T's in attract. Why did I doubt myself? Never change your answer on an exam. All right, they attract each other, all right, because they have opposite charges. So, I have a second question. If you were to move an electron away from the nucleus, so if you took an electron right here and you moved it here, I'm going to scoot this over so I have a little more room to work with. So if we took our electron and we move it away, away from the nucleus. So we move it so that it's farther out. Would this be endothermic? Or would this be exothermic? Think carefully. Endothermic or exothermic? Now, let me put it to you a different way. If you're like, I have no clue. Let me put it to you a different way. If you take does the electron want to be close to the proton or far away? And the answer there is it wants to be close because it's attracted, right? So to take that proton and pull it away from, to take that electron and pull it away from the proton it's attracted to, you're going to have to exert a force, right? You're going to have to pull. Yeah, totally. I'm seeing a trifecta of endothermic responses. That is 100% correct. If you move an electron away from the nucleus, that process is endothermic. All right? Now, I've got another question. If you take your electron and move it closer to the nucleus, if the electron gets closer to the nucleus, is this process endothermic or exothermic? All right, and if moving the electron away from the nucleus, you're pulling it, you're exerting energy to move it away from the nucleus. If that's endothermic, then getting closer to the nucleus must be exothermic. All right? Now, because if one's true, the reverse has to be correct. So check this out. When an electron moves away from the nucleus, when an electron moves away from the nucleus, the atom absorbs energy. When an electron moves away from the nucleus, the atom absorbs energy. Oh, wait. I did not want to do that in green. I wanted to do that in yellow to keep my... Whoa. Color scheme, all right. Hang on. There we go. So when an electron moves away from the nucleus, the atom absorbs energy. And when an electron moves closer to the nucleus, our atom releases energy. All right. I thought this was going to do something with the orbital blocks or whatever they're called. Let's see. Salvesandon. That's where we're headed eventually, but right now we're building towards it. First with the discussion of atomic emission. So we move an electron closer to the nucleus. It's exothermic. Our atom releases energy. When we move our electron further from the nucleus, our atom is absorbing energy because it's endothermic. Neutrons, question mark. Here we're talking about a hydrogen atom, so there are no neutrons in the nucleus of a hydrogen atom. Now, here's why this is conceptually... Oh, salvage. Okay, sorry. I didn't know, Sorry about that. Where the break was. So YouTube handles can be hard to read sometimes. All right, cool. So the reason why this is important to understand conceptually is it ties into what took us from the Rutherford model of the atom, which I have drawn here, to the Bohr model of the atom, which is kind of like the baby version of the quantum mechanical model. All right. Now, in the... Oh, goodness. Where did my lecture notes go? Here we are. Now, here's why this is clutch. So it turns out that the energy released and absorbed by an atom's electrons is light waves, or I should say are light waves. The energy absorbed or released are light waves. And theoretically, it's possible for an atom to absorb or release, theoretically, any type of light, because theoretically the electron could move any distance. The further you pull the electron away from the nucleus, the more energy it's going to absorb. The further the electron moves closer to the nucleus, the more energy, the larger quantity of energy it's going to release. But when the hydrogen atom was studied, it didn't release a broad spectrum of light. What we actually observed is that atoms only release specific wavelengths of light. Specific wavelengths of light. And the question this prompted is why? Why do atoms only absorb specific wavelengths of light? And the Bohr model of the atom attempted to explain this by introducing a feature called an orbit. So again, I'm going to draw a hydrogen atom. So we've got our proton. We have our electron. All right. Now, this is the Rutherford model. The Bohr model is pretty much the same, except it adds this feature called an orbit, where the electron in the Rutherford model is just spinning around in this circle. In the Bohr model, there are concentric orbits, and I apologize, these should all be, you know, circles. It's you're getting my best stabs at it. And so this being the Bohr model, Niels Bohr proposed that the electron orbiting the nucleus was not free to orbit at any given distance it wanted, that it could only orbit at these preset lengths. And he named each orbit using the letter N, and he said N1, N2, N3, and N4. Great question. Do the specific wavelengths of light depend upon the proton count? And the answer to that question, Salvesh, is actually, indirectly it does. The specific wavelengths of light that an atom will emit is determined by the electrons, because the electrons are the things that are moving further away and then closer to the nucleus. But the number of electrons that an atom has is determined by the number of protons in the nucleus. So directly, the electrons are what determine the types of light that get absorbed and released. But in an indirect way, the protons are what are attracting the electrons to that atom itself. So they bring the electrons, and then the electrons govern what types of light are released and absorbed. And you'll see how in just a minute. So the reason why this model was adopted is because it could explain why only specific light waves were seen to be absorbed or emitted. And here's what I'm talking about. So if your hydrogen, so when you irradiate hydrogen with a ton of energy, its electrons are able to absorb that energy and move from a close orbit out to a more remote orbit. All right, this process, when an atom when an electron absorbs energy and moves from a low energy orbit to a high energy orbit, we say that the electron is, so this is called adsorption. And no, I did not spell that wrong. So we say that this process is called adsorption, and we say that the electron is in an excited state. All right. So there's the ground state, which is the lowest energy possible. So this electron right here is in the ground state. This is called, I've got running out of places to write this, the ground state, because it's the lowest energy possible. All right, so that's the ground state. Any time an electron is not in its lowest energy orbit, we say that it's in an excited state. All right, so The adsorption process happens. The electron's in an excited state. But as we know, the electron's attracted to the proton, right? It's attracted to the nucleus. When it absorbs energy, it'll hang out there in that excited state for a while, but it wants to come back home. It wants to get back with the proton. So the inverse process is going to take place. The electron is going to, so we said that it's become excited. It will de-excite and move down to a lower energy orbit. But here's the question. Which orbit is it going to move to? See, the electron now has a choice. It's out in energy orbit 4. It can move to the first orbit, the second orbit, the third orbit. There's choices. And as we know, the farther it moves, the more energy it's going to release. And those different energy levels will be different wavelengths of light. So, for example, if our electron, all the way out here now in its excited state, decides to move down to the first orbit. So it moves back. To do that, that is a exothermic process, which means energy is going to be released. And it'll release a certain frequency of light, and that frequency will determine the wavelength of light, and that wavelength will correspond to a specific color. All right, so this, if it moves down to the first energy level, it'll release a color of light. If it moves to n equals 2, this emission will release a different frequency of light, and therefore a different color of light. If it moves down, oops, I didn't mean to pick green, to n equals 4, this will emit a different color of light. All right? And so these orbits were actually calculated based on the frequencies of light and how far the electron would have to travel to release a light wave of that specific energy. Oh, did I misspell Planck's name? It looks like... Oh, man. I've disgraced my ancestors. So for those of you tuning in, I misspelled Planck's name a while back. I've disgraced my chemical ancestors, and I'll probably be haunted by the ghosts of dead physicists for years now. All right, so these orbits, this is why specific atoms only release specific wavelengths of light. These orbit distances were calculated to match those energy levels of light that we see being emitted. And so it was a huge breakthrough. And when you think about it, it's counterintuitive. It's super weird to think that an electron is not free to be any distance from the nucleus, that it can only be at specific preset wavelengths. It's either at N1, N2, N3, or N4. So the electron's orbits are very 8-bit. It's very Minecraft. It's not smooth. It's just these bricks. It's like stair step up, stair step up, stair step up. And that phenomenon, we say that the energy orbits of an electron are quantized. That's where that word quantum comes from. We say that these have a quantized energy. So when you hear the word quantum, literally think Minecraft. We're not thinking smooth curves, analog curves. We're thinking digital pixelation of energy. That's what quantized means. All right, so it's not a scary word. Now you know. So this was a huge breakthrough in our understanding of atomic structure. And yeah, Viraj, just like you said, this leads to Lehman, Balmer, Rydberg, all that stuff. Yep, that is exactly where we're going. Other physicists got super pumped about the Bohr model of the atom, and as scientists do, we wanted to explain the world we live in mathematically, which this was done by two dudes named Balmer and Rydberg. Balmer and Rydberg. Let's see, do the electrons release colors that are invisible as well? Okay, excellent. Salvage, excellent question. So the question is, do electrons release colors that are invisible as well? And the answer is yes. When we were developing, or not we, I didn't have a part in this, when the physicists of yesteryear were developing the this new revising our model of the atom, they were basing their model off of visible spectrum, but turns out there are a ton of different transitions. Something that I didn't even touch on is, I was just showing you, for example, transitions from n equals 4 to n equals 1, or n equals 4 to n equals 2, 3 to 4. But you could also, if you jumped from 3 to 4, you could jump from 3 to 2 or 3 to 1. There's, tons of different types of emissions. X-ray, ultraviolet, all types of stuff that are not visible to the naked eye. So yes, those totally do happen. We just don't see them with our eyeballs. We have to use other methods of detection. So, but based on the visible spectrum, the Balmer-Rydberg equation was the first attempt to mathematically develop an equation that could describe and calculate the energy of transitions, of the transitions that we saw in a hydrogen atom. So let me bounce back one slide. Sorry, one last thing I wanted to touch on before we leave this slide. So when we talk about an atom, an electron moving closer to the nucleus, releasing energy, these are called atomic emissions. All right, that release of energy is called an atomic emission when an electron is de-excited from an excited state. All right. So Balmer-Rydberg developed a mathematical expression to calculate the energy of the photons of light that were being released by emission. Yeah, okay, sorry. Gregory, does the wavelength of light go up based on how far the electron goes in? Yes, because the energy of the photon of light released depends upon how far the electron travels. So if an electron travels a short distance, the energy is low, which means the wavelength would be high. If the electron jumps a large distance, the energy will be high, which means the wavelength will be low. So absolutely, the wavelength of light is determined by the distance traveled by the electron. All right, now the original formulation of the Balmer-Rydberg equation actually didn't have energy in it. They developed a relationship that said the inverse of a wavelength of light is equal to r, which is a constant, times 1 over the initial orbit squared minus 1 over the final orbit squared. All right. And so they said if you take the inverse squared difference of the initial and final orbits that are traveled, multiply by this constant, that's equal to the inverse wavelength. Now, this equation is not used that frequently because it's frankly not that helpful. Nobody really is interested in inverse wavelengths. But the cool thing is we can give this an algebraic massage to put it in a more usable form. So, oh, sorry, I see I've got a question. Do 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 do. So okay, sorry. Vraj has a question about Heisenberg uncertainty. Oh wait, hang on. Where are we? Okay, so Vraj, your question says that Heisenberg uncertainty principle says that we can't judge the acute movement of an electron. Then how can we pinpoint the numbers that accurately? So Heisenberg uncertainty principle actually says that you cannot know. It's a relationship between the energy of an electron and the position of an electron, and it says that and there's this relationship that the more information, the more certain you are about the position, the less certain you are about its energy, and the less certain you are about its energy, the more certain you can be about its position. But what it's saying that relationship is specifically talking about an electron in a specific orbital, and we'll talk about that in a little bit, probably next lecture. That's talking about an electron in a specific orbital. It's not talking about an electron traversing a distance in space. So based on the fact that we know the electron's charge and the electron is moving in relationship to a proton, when two charged particles change position in space, you can use Coulomb's law to calculate the energy change that will accompany that movement. So Heisenberg is talking about the momentum and kinetic energy that an electron has as it rests in an orbital. But when we talk about it moving closer to or further away from a proton, we can use Coulomb's law to calculate that energy difference. Totally. That was an excellent question. Excellent question. So we're dealing here with kind of classic Newtonian particle physics, and then we'll talk about the development of quantum mechanics and orbitals and uncertainty, and all that is to come. But right now we're kind of in a safe Newtonian world where everything's a particle, which is a round little ball. Okay, great question. So this was the initial formulation of the Balmer-Rydberg expression, and I levied this criticism against it that inverse wavelength is not that helpful of a unit, and I maintain that. But check this out. We can rearrange our apartment using algebra. If you look at the equation for the constant speed of light is equal to frequency times wavelength. Let's do something fun. Let's divide both sides of this expression by lambda. All right, and actually, I'm going to do that in a kind of funky way. I'm going to multiply by 1 over lambda on both sides. So what happens on the left side is lambda cancels. This gives us an expression 1 over lambda, or I should say c over lambda, is equal to frequency. Now, next algebraic step, I'm going to multiply both sides by 1 over c. So c cancels with c, and we get 1 over lambda is equal to frequency divided by the constant speed of light. I don't know if you can hear that on the recording, but my 1-year-old has woke up with a fever this morning, so he's kind of in misery. Now, if you look at this expression, you can see that we've solved for 1 over lambda, which means we can substitute in to the original Balmer Rydberg equation. Here, Sorry about that. He's feeling miserable. Just a baseline, but he fell down and took a spill. So that was sad. Okay, so we can substitute this expression in to the Balmer-Rydberg equation, the original one, and when we do, we get frequency over the constant speed of light is equal to this R Rydberg constant times 1 over our initial orbit squared minus 1 over our final orbit squared. All right, now again, this may not look like the most, this may not look particularly better than our previous formulation, but we can continue to do a little algebraic massage. We're going to multiply both sides of this expression by the constant speed of light. It'll cancel here, and we get frequency is equal to R times C over 1 over N1 squared minus 1 over N2 squared. All right, and now we're going to do something that may seem like the strangest, most random algebraic maneuver yet, but I'm going to multiply both sides of this equation by Planck's constant. And if you're wondering why the heck would we ever want to do that, it's because energy is equal to Planck's constant times frequency. And we can substitute this in for this. So that gives us a way more user-friendly version of this equation where it's energy is equal to R times C times H times 1 over N1 squared minus 1 over N2 squared. All right. Okay, let's see. We've got some questions. What do we also compile? Yep, as you actually anticipated my move. Now, there's one last thing we can do to simplify this. One thing you may notice when you look at this equation is R is a constant, C is a constant, H is a constant. What happens when you multiply a constant number times a constant number times a constant number? You just get a different constant number. And so when you multiply, so these are all combined into a constant that they named RH, all right? And RH is equal to 2.18 times 10 to the negative 18 joules. All right, so this is a little more user-friendly and gives us the final formulation of the equation, which is E is equal to RH times 1 over N1 squared minus 1 over N2 squared. All right, and this is the version of the Balmer-Rydberg equation that I put on the front of the exam, and this is the one that we'll be using to do our next example here. Sorry, there's a flurry of comments. Let me catch up on them real quick. Salvish, you just dropped the best piece of exam taking wisdom that anyone could hear, and that is never. Whoa, where am I? I'm over here. Never change your first answer. That is money right there. All right, now with this, let's see. Do we really need these derivations, or are you mainly showing them for us to get an idea of where? Yep, that is, Ryan. That is exactly what I'm doing. You're not going to see a problem on the exam where I'm going to say derive the more user-friendly version of the Balmer-Rydberg equation from the less user-friendly one. I'm just giving you a sense of where they come from, and also how these all equations all connect to each other. Like here we pulled in, another instance of our energy is equal to Planck's constant times frequency thing. So I think it's instructive to do, and also this is the type of algebra that's Gen Chem bread and butter. All right, but let's use this to actually do an example. All right, so let's check this out. So we have a new example. So a hydrogen atom emits a photon of light when an electron transitions from the orbit n equals 3 to n equals 2. Determine the energy of that photon. All right. Now, Balmer-Rydberg problems are all very straightforward to do because you just need the Balmer-Rydberg equation. The energy of the transition is going to equal RH, right? That's the combo, times 1 over the initial orbit squared minus 1 over the final orbit squared. All right. Now, for sig figs, something you should know is these orbits are exact. All right. They're exact, not measured. We're saying from the first orbit to the second, or we're saying in this problem from the third orbit to the second, right? So they will never limit your sig figs. The Rydberg constant, however, is a measured quantity. This is a measured quantity, so you've got to take care of your sig figs here. All right, so that's something to just watch out for when you're doing these calculations. Now, I'm going to wait to plug in RH till the end, and let's plug in our value. So our initial orbit here is our third. Our final orbit is our second. So we've got RH times 1 over 9 minus 1 over 4. So if we have 1/9 minus 1/4, that'll give us, now RH is 2.18 times 10 to the negative 18 joules. That's our value for RH, times 1/9 minus 1/4 is 0.138 forever. And I'm going to use that whole number. I'm not rounding at all because this, again, is exact. We multiply that. Oh, sorry, this is a negative 0.138 forever. Multiply this by 2.1 0.18 times 10 to the 18, 10 to the negative 18, excuse me, gives us an energy of negative 3.027 forever times 10 to the negative 19th. All right, but we can only keep 3 significant figures because our Rydberg constant only has 3 significant figures. So the final answer here for our energy will be negative 3.03. Come on, there we go. Negative 3.03 times 10 to the negative 19 joules is the energy of that photon of light. All right, so a couple things. First, if you're freaked out by this negative sign, don't be. Because we moved from a high energy orbit to a low energy orbit, which makes this process exothermic. Right? This process is exothermic, so it should have a negative energy value, right? Will you ever give us a question where we have to find the transition of an electron based on energy? Yeah, Salvish. Okay, so Salvish's question, would I ever give you a question where you would have to find the transition of an electron based on energy? I totally could. If I did, though I would say, if I did, I would also give you either your starting orbit or your final orbit. I'd give you your initial or your final. So it wouldn't be like, find any number, but you'd have one of those two variables. So you'd have one equation, one variable. You wouldn't have to guess and check. But that's, so in that instance, that's totally something that could happen. Cool. Other questions? There we go. Okay. So that is the Balmer-Rydberg equation. It's fairly... sorry. I almost said loser-friendly. It's user-friendly. Easy to use. Nothing too hard about it. Now here's... So far, the story's been awesome. We've revised our understanding of atomic structure. We know that the orbit energies are quantized. Electrons can be in one, not the other, but no space in between, and we have data to back that up. It's been an awesome story so far. Super useful. And to be honest, at this point in time, physicists, the community of chemical physicists were ripping high at this point. They thought it was awesome. They're like, we can use math to explain everything. And they were about to get a huge letdown. So let's talk about some of the drawbacks to the Balmer-Rydberg equation. All right, Balmer-Rydberg drawbacks. So this equation was developed by studying the hydrogen atom. All right, it was developed by studying the hydrogen atom. And one thing we know about hydrogen is it has one proton and one electron. Ooh, that might be my worst circle ever. Slightly better. Not much. Actually, sorry, this is going to bother me. All right, there we go. Here. I think my problem was I drew the electron, so I felt the need to like run it through that point. There we go. So the Balmer-Rydberg equation was developed by studying the hydrogen atom. They were super pumped. They're like, we have this mathematical equation that can explain the energy of transitions. We can predict them. Let's go do other elements on the periodic table. The next element to try naturally after hydrogen would be helium. And for hydrogen, totally checks out. All right? Excellent equation. When they moved to helium, and they're like, can we predict using this equation? Let's predict the energies that helium will emit, the light energies. And it was an epic fail. They tried to predict the emission energies for helium, the wavelengths, types of light, and did not work at all. Not one of them. They tried moving to lithium. They tried other elements, and their equation did not work for anything other than hydrogen. Which, if you look at the periodic table, you basically have an equation that works for 1 out of 112 atoms, right? It was really, really sad because they went from this thing like math can explain everything to math can explain almost nothing. But it propelled us as a community of chemists to ask a very important question. Why? Or just H and half of a Y. There we go. Why does it only work for hydrogen? And answering that question propelled us from the Bohr model of the atom, where we had electrons orbiting a nucleus in these two-dimensional orbits, into the quantum mechanical model of the atom. Now, there are two reasons why this didn't work. The first was one of the number of electrons. So hydrogen, is the only element on the periodic table that only has one electron. And turns out that for helium or any other element, when you have multiple electrons orbiting an atom, there's two interactions. In hydrogen, there's only the attraction between the proton and the nucleus. For every other element, there is that attraction, but there's also electron-electron repulsion, right? You've got multiple negative charges that are all pulled in close to that attraction to the nucleus, but they're also repelling each other, right? It's kind of like a concert where you're trying to like wedge your way as close as you can to the band, but you're getting pushed back from all the other people, all the other electrons who are around you who are also trying to get close to that band. And so every other element, so it turns out that that electron repulsion changes the orbit energies. All right. Electron-electron repulsion changes the orbit energies. That's one of the reasons why this equation failed to predict the emissions for atoms with multiple electrons. The second reason is that electrons, even though their orbits are quantized, they actually move in 3 dimensions, not 2. And there was an assumption with the Balmer-Rydberg equation that the electron was moving in a 2-dimensional orbit. Turns out it's moving in a 3-dimensional orbit. That raises the question, well then, if electrons move in 3 dimensions, why did it work for hydrogen? And as we'll discuss next lecture, hydrogen's electron is housed in a 3-dimensional s orbital, which is spherical, and turns out that a circle was a close enough approximation of a sphere to accurately predict the energy transmissions that we see for hydrogen. So it worked for hydrogen because it's a special case. As we'll learn in next lecture, other elements have different shaped orbitals. Not every electron's orbiting in a 3-dimensional spherical shape, and that is another reason why this equation falls short for the rest of the periodic table. All right, so these are the drawbacks to the Balmer-Rydberg equation. You'll notice that every problem that you do in the homework based on Balmer-Rydberg will always say for a hydrogen atom, because these only work in systems for atoms that only have 1 electron. There's only 1 atom that has 1 electron. But it was very, very important because it got us to conceptually to the place where we understood that the orbits of an atom were quantized, that the electron wasn't free to be anywhere in space. It could be at energy level 1 or energy level 2 or energy level 3, and that set the stage for what our current understanding of atomic structure, which is the quantum mechanical model of the atom. All right, that's what we're going to be heading into next lecture, is seeing that this has just been built up to that moment. Okay, Salvesh has a question. Multiple electrons equal multiple emissions? Well, yes, they do, but we actually saw with hydrogen, even though there's only 1 electron, there are multiple emissions possible. So 1 electron doesn't mean 1 emission. There's multiple emissions for the 1 electron, but the emissions get more as we do build electrons. Okay, Macy, you got to go to class. Totally cool. You can tune back in. We're going to talk about the exam a little bit right now, so I will time mark it so you can just pop right to this moment on the video. Okay, so that is the end of our lecture today, and so let's talk a little bit about exam 2. Oops. Undo that. New slide. Oh, wait, is this not? Here we go. All right, so here, here's what I know about exam number 2. The material that we're going to cover will be as follows. It will be chapter 5, which is our gas laws. Chapter 6, which is thermo. And then chapter thermo, there we go. Chapter 7, not the entire chapter, just through today. Photoshop's being a little laggy. Oh, that's ugly. All right, so exam 2 will be chapter 5, chapter 6, and then chapter 7 through today's lecture. Oh, sorry, Salvish. Sorry, bumping back. You said all the electrons are able to release energy. Yes, that is totally true. All right. So also something to remember on exam 1, everybody, not everybody, but most people kind of bombed the redox problem. So it is coming back. You can expect to see it show up on exam 2 as well. So I would dust off those skills and practice balancing some redox reactions using the half reaction method. That is the material that will be covered on the exam. As you know, in the syllabus, it states that each exam is worth 120 points. And these points will be divided between the two portions of the exam. There will be a Canvas portion, and then a take-home portion of the test. Oops. Canvas and take-home. So each half of the exam will be worth half of the points. So the Canvas will be worth 60 points. The take-home will also be worth 60 points. I decided to weight them evenly. I don't know if I'll continue to do this for exam 3, but for now I thought that would be the best way to go. Make them worth the same amount of points. The Canvas quiz will be multiple choice. The take-home will be exactly like the in-class exam. It'll be a long answer. All right, so you'll, be doing calculations, all that good jazz. The Canvas exam will be timed. I haven't decided exactly, but I'm planning at this moment to make it a 40-minute quiz. Oh, let me fill in multiple choice. The take-home, you'll have 24 hours to complete it. So you'll have a day. I'll be emailing them out, and you'll have a 24 hours to complete it. So the Canvas one, you obviously complete by you log in and take it. For the let's see. There we go. For the take-home, you log in and take it for the Canvas. Sorry, Photoshop's being super laggy today. For the take-home exam, I'm going to email it. Oops. I'm going to email it to your Los Rios email account. So if you are not in the habit of checking your Los Rios email account, you will want to, because this is the vehicle through which you're going to be getting the exam. So through your Los Rios email, the reason why I will be sending it to that email is because I'll also be sending it from my Los Rios email account, and that will ensure that it goes into no one's spam folder. All right. So you'll need to log into your Los Rios email and then download the PDF attachment and take it. You could, if you have the ability to take it digitally, like if you have some sort of stylus based computing device, you could totally can do that. You can print it up, take it, and then send it back to me. Now, the way you're going to submit your take home is you submit it through email again. All right, so you take it, you send it back to me. If you took it physically and you have a scanner, that would be awesome. But I'm not going to make that a requirement because not everyone may have access to a scanner. But you can snap photos with your phone and send it to me. Note that even though I'm accepting phone photos, whichever one gets submitted by the deadline is the one I'm grading, and if the photo quality is not good enough to be able to read what you've written, then you're not going to be able to get points. So make sure you take the best picture possible, because if it's not good and I can't read it, you're just going to get 0 on the problem. Okay, so let's see. Wow, we've got a bunch of... Wow, death skulls, corona. Would the canvas one be different for all of us, or will it be the same but shuffled? Excellent question. Is the canvas one going to be identical, or is it going to be shuffled? And the answer to that is I'm currently building a problem pool. So if you're looking for someone to be the sacrificial lamb to take it first and then tell everyone what was on each problem, there is going to be a bank of problems of all the same type that Canvas will select from and shuffle through. So everyone's tests will be range from slightly to completely different, but all with the same caliber, same difficulty problems. So yeah. So let me type my response as well. Choice will, yeah. That's awesome. Yes, you can't use Salvesh anymore, Raj. You guys will have different quizzes. So that's the what I know at this point in time. I don't have a total problem count for the Canvas multiple choice quiz yet. mostly because I'm still building the problem bank. I also don't know how many problems long the take-home portion will be, but you can imagine, because you have 24 hours to complete it, that it's probably not going to be short. Why am I always the sacrifice? That is a good question. Maybe you guys should like roll dice, or play rock paper scissors, cause you the goat, to determine who needs to be the sacrifice. Well, nobody has to be sacrificed because everybody gets to take a different quiz. How cool is that? Also, I will be sending out different forms of the take home, so not everyone will have the same version of the take home. And I know I've said this before, but the take home exam, because I have no way to proctor it or monitor it, will be open textbook, open internet, open other humans. There's no restriction on who you can talk to, what you can use, all that stuff. But as a result, I'm planning on writing 4 different versions of it. So again, they're all going to be problems of similar. And that, when I say 4 different versions of it, I'm not talking about different numbers, but like 4 different versions of similar caliber problems, but different. So not everybody will take the same take home. That'll be somewhat randomized as well, though my ability to randomize that is not as great as my ability to randomize the Canvas problem bank. So that's another thing that will be in play. Do you guys have any other questions about the exam or otherwise? Let's see. I don't know. So I know some people joined in for the. That's tough. Yes, totally is tough. I know some people joined us. So here's a. Some people joined us for. We held our first electronic office hours, on, last. What was that? Friday. Hours. And we had a few people in live, which was awesome. We also had some people tuned in and watched later. Just a reminder, we will be doing it again on Friday. So it's going to be every Friday at 1. All right, so tune in if you can, watch later if you can't. Let's see. So one thing, actually, Jesse, I'll answer that in just 1 second, but I just want to put a reminder. When you send in your questions for the online office hours, remember to include, if you're include a subject line of Chem 400 office hours. That will make sure that I do not miss your that I don't miss your question, that I can get it and include it in the office hour. And then also, so have a subject line, Chem 400 office hours, and then please include a picture of the problem. That way I don't have to be flipping through the textbook, and it will make the stream a little more fluid. Okay, let's see. We've got We've got some questions. Okay, so Jesse, let's see. Okay, sorry, I gotta catch up on these comments. When is the exam being sent out? Okay, Brandon, when is the exam being sent home? Oh my gosh, sorry. I just looked at what Photoshop is doing. You'll be seeing it in a second. I said, please include a pic of this is evidence of demon possession, I'm pretty sure. Please include a picture of the problem. I guess I got writing a little fast for Photoshop. Oh my goodness. Let's see. The problem. Okay, so Braden, when is the exam sent out? Okay, so the Canvas multiple choice will be available to take within a 24-hour period, and you'll have 40 minutes to complete, which is half of our normal timed exam time. So there will be a 24-hour window in which you can log in and take the Canvas exam. So you can do that portion of it at your leisure within that 24-hour period. The what's the word I'm looking for? The take-home portion of the exam, which I'll be personally emailing to each student, which will be super fun, will go out. I'm going to be doing a probably an automated, like, send this at this time. It will go out. Yeah, I haven't actually. That's a good question. I haven't decided the specific time I'm going to send it out. I know our exam day is a week from today, so on the 30th. So I will probably choose to. I haven't decided whether or not I want to send it out at midnight, or a little bit before. But whenever I do choose to send it out, you will have a 24-hour, at least 24 hours to do it. It'll be due at 11:59 March 30th, so that's Monday night. I might see if I can set up an automated, like, email thing to send it automatically out at midnight on Sunday. Maybe I'll send it out with a little lead time so you'll get it earlier Sunday evening. I haven't quite decided, but you're going to have at least 24 hours, and it'll be due at 11:59 Monday night. So I guess the answer to your question is I don't know exactly when the exam is being sent out, but I'll have more information on that in the future. Let's see. How does this... I don't know how this relates to Hawkins radiation, to be honest. Okay, Jesse, how do we get in touch with our lab professor when he doesn't respond? I understand that you're not him, but still, he has Zoom. He did a conference, but he didn't know what to do. How to access that? I've tried adding him. Okay. Jesse, I can imagine that's frustrating. I know all of us faculty have definitely been scrambling, and some of us may be more tech adept than others. I can totally reach out to your. I'll reach out to both lab instructors and just give them the heads up that that I'm hearing that some of you are having a frustrating time getting in contact with them, and encourage them to be more prompt, due to the fact that this is we're in a 100% digital zone. So I'll reach out. I'm sorry that your lab instructor hasn't been as on top of it. Okay, let's see. Exam date. Jake wants to know when the test is. That's great. That's a great question to have. Um, so exam 2 is a week from today. I made a post on Canvas about it, but maybe you didn't see it. It will be on the 30th of March this year. So it'll be a week from today on Monday. Let's see. Okay, did you guys find the lab videos? Okay, sweet. Let's see. Type lab and work docs, definitely. Okay. Oh, I already answered. So, okay, cool. Cool beans. Yep, so that is our exam. It'll be an experiment. I'm interested to see how it goes. Any other questions or concerns? Let's see, we're running 17 minutes over. Cool. So let's see. I was hoping. I'm sorry to let you down, Brandon, but it's actually this year, March 30th, which means we have less studying time to do. So for Photoshop. Excellent, interesting question, Salvesh. So I use I have a Microsoft Surface Book that I use to draw in Photoshop when I'm live casting these things. Yeah, totally. Stylus on a Surface. It's I've never been good at mouse drawing in Photoshop. There's something about it that it just always look like it always looks like I'm a 6-year-old when I try to do that. What if you get coronavirus on the 30th? That's a great question. That's a great question. I think that's what you do, Ace 159. I think you just take it when sick. So yeah, so let's not get coronavirus on the 30th. Yeah, I think I'm just gonna say take it. I think take it sick is actually the right answer. Because mouse sucks on Photoshop. Totally sucks. Because I'm pretty sure if you didn't have to take it sick, then everyone would probably get coronavirus on the 30th. So probably everyone will, but we'll all just have to take it sick, and it'll be an even playing field. Totally. Other questions. I kind of like this post-lecture hang time. It's kind of cool and informal, which is cool. Alrighty. So on what day is today? Today is Monday. On Wednesday, my plan is I'll continue. I'm gonna do a little bit of Salvage has okay. I'll trying your best to get coronavirus on the 30th. Go outside. Go to a hospital and lick all the door handles. Would be a pretty surefire way to come down with corona. Yeah, you got to keep a future sacrifice in your back pocket. You know what I'm saying? On Wednesday for our lecture, I think what I'm going to be doing, we'll do some more quantum lecture. That material will not be on the exam. But I'm not going to lecture for the whole time. I'm going to lecture for part of it, and then do a bit of a breakdown of the exam. Give you more specifics on like this is the percentage of this concept, that sort of thing, and so I'll have more kind of info on the exam. I'm currently writing. I've been writing it. I actually started it over this weekend because I've got to build a problem bank, which is a little bit of a pain in the butt. But I'll have more information about the points breakdown for both the multiple choice and the take home, and And what I'm going to normally I take the lecture before the exam to do kind of a review and go over problems, but I'm actually not going to do that with this lecture. Instead, send your questions in, and we'll talk about them during office hours. So our office hours this Friday will be our exam review. So start studying. Email me the problems that you're having trouble with, and we'll go over it on Friday. Let's see, how's quarantine going? Dude, you work at the grocery store. Nice. You can snag all the bagels when they put them out. My kids are like, "Did you check for bagels?" I'm like, "Yep, we're still in the bagel drought, kids." Quarantine's not going too bad, except for the bagel drought. I have been actually right before quarantine crackdown. My nephew has a one wheel, and I rode his a few months ago, a couple times, and loved it. And I finally found one used, and I bought it. And then it was quarantine, so I've been riding my one wheel, doing digital things with you guys, and watching anime with my kids. It's not been a bad quarantine so far, except for my baby's been sick twice. He was sick a few weeks ago, and he's got another fever today, which is awesome. And my wife was also sick, because she's a nurse and works at the hospital, which is the best place to be going to during quarantine. So, mixed bag. My Hero Academia is awesome. You guys have been awesome to hang out with online, and riding a one wheel is awesome. Not too bad. Virtual cough. We do have to work. We have to watch so that we don't virtually cough on each other. Let's see. Part of my job where I work. I have not watched JoJo. Is JoJo a cool anime? Dude, I would love to longboard with you. Do I play games, Prof? Oh yeah, so I do play games, all kind of games. I love board games. My wife and I are huge tabletop gamers. So we play all sorts of things. From probably our main is Magic the Gathering. She and I both. She's better than I am, which is aggravating. But also fun because it means I'm challenged. I don't know if I am able to challenge her. Oh, have I seen JoJo? So I play. Yeah. I play Warhammer 40K. We play Pandemic, an appropriate board game to be playing right now. D&D, the whole gambit. Oh, do I play the video games? I'm only a casual gamer. I have an addiction, and I've had to step back from video games because they have the potential of taking over my life. So I pretty much limit myself. I'll play Mario Kart and Smash Bros with my kids. There was a while I did a deep dive. The last two times I got really into a game was Breath of the Wild, and Pokemon Sword. I couldn't help myself because I've been playing since Pokemon Blue, so I had to get into that. Brayden, let me tell you more about this Magic the Gathering I speak of. It is a customizable card game based on 4 magical color domains, and you build a deck and duel other planeswalkers. Oh, you have a Magic the Gathering card as your profile picture? Now I have to get closer. I can't tell what it is. Brayden, what? Oh, no, now I know. You've got Chiller Pillar. That is awesome. Now I recognize it. Yeah, dude, if you guys play Modern Warfare, you should totally play with each other. That'd be rad. Oh my gosh, what's happening? Sorry. Yeah, we just went down a rabbit hole. Quarantine survival tips. Plant a garden. That is great advice. Great advice. We are basically hanging out. I actually now that I that brought my attention to the clock. I need to run, um, see what's going on with the fam. I have to do some fun errands today, which means I get to leave the house, which is good. Hopefully before the rain rolls in. Anyways, you guys have been awesome. As always, I will see you all on Wednesday. Send in your questions. We're gonna do a bomb exam review on Friday. Oh, sorry, I just realized I never responded to Ace. Ace 159. Um, I have not yet seen Jojo Rabbit, but I'm dying to. Um, I've loved Taika Waititi ever since I saw What We Do in the Shadows. Um, it's an amazing movie. Okay, let's see. Yeah, we're just hanging out. Best tip so far is not to die in times like these. That's good advice. Good advice. Let's stay alive, and continue this weird digital online education thing through YouTube. Um, Anyways, I gotta run. Thank you all for hanging out. I will see you all on Wednesday, and send in your questions so we can do a dope exam review in office hours this Friday. I will catch you guys in 48 hours.